What is this? Oh, that's my collection of resistors. Not that one. This one. What is this? Oh, we have LED here. Yellow LED, 10mm, and some resistors here. And a transistor, a push button with a power supply of 5 volts here. And we're going to push the button. LED lights on. Push the button. LED on. Release. Kill the light. Push the button. LED on. Release. Oh, we have a new circuit. This is a circuit transistor as a switch. My version 3. Let's see the circuit. So this one is my version 3 of a transistor as a switch. This one is my version 1. The LED is in series with the supply. See the other version. This one is my version 2. The LED on the collector side. And this new circuit is my version 3. LED is in the emitter side. So we don't know the value. I put resistor here, here. This is a pull-up resistor to balance the circuit. This one is base resistor to limit the current in the transistor. This one is pull-down resistor for the possible leakage current. And this one is the current limiting resistor of the LED. Okay, compute R3. This one using Kirchhoff's voltage loop, my favorite magician. Voltage supply minus voltage supply plus voltage drop here. Voltage drop the collector to emitter saturation is 0.3 volts. That's in the table. Collector to emitter saturation 0.3. That's 0.3. Then the voltage drop across the diode, and that is 2.0 volts. That is in the data sheet of the LED. In order to turn the LED, must have 2 volts forward voltage. Now we get this voltage across R1 and voltage drop across R3 is equal to 2.7 volts. We all know that this voltage is equal to this total voltage. So we know the voltage drop here and here. So we need the voltage in series. We don't know the value of resistor here. So since this is 5 volts and we know the resistance of the other two components, so we get to divide that 2 resistor for the 2 resistor. So since 5 volts minus 2.7, the voltage drop across the transistor and the diode, 5 volts minus 2.7 is equal to 2.3. That is the remaining voltage drop across here. We divide that into 2 for this 2 resistor. So we got 2.3 divided by 2 is equal to 1.15. Each have voltage drop of 1.15 volts here. Voltage drop here, voltage drop here. We know the voltage drop across the resistor 3. We now compute for the R3 using Ohm's law, my favorite magician. Voltage drop over a current 57.5 ohms. That is 100 ohms, my available resistor. Computing for R1 here. So we use the transistor magic formula. Since we know that the current at the diode, we're going to pass 20 milliampere here. So it means the current flowing here is 20 milliampere. We know now the current across R1 is equal to 20 milliampere or 0.02 ampere. So Ohm's law again, my favorite magician. Resistor 1, voltage drop plus R1. We know that here 1.15 volts divided by 0.02 is equal to the same as the resistor here, since we divide the voltage drop each. Find resistor 2 here, the base resistance, to limit the current in transistor to operate in saturation mode. So transistor magic formula, IB is equal to IC over HFE. HFE here is 60 from the table. Since we're operating in 20 milliamps, under here the HFE is 60. So 60, 0 point, the collector current is the current flowing here to saturate the transistor. 0.02 divided by 60 is now equal to 0.0033 ampere. Now Kirchhoff's voltage loop across R2. Going to voltage loop here, here, and here, over there. So minus Bs plus voltage drop C, voltage drop base to emitter saturation mode is here. Base to emitter saturation mode, this one, under 20 milliampere, I have 0.95 volts. So we got now this formula. Volt Bs means voltage drops here, voltage drops BBE, voltage drops PR3, voltage drops across RD, completing the loop. Because according to Kirchhoff's, all voltage in a loop is equal to 0. The sum of all voltages in a loop is equal to 0. Now, computing for voltage drop across R2 is now 5 minus the BBE saturation minus the voltage drop across resistor 3 and minus voltage across the LED is 0.90 volts. Ohm's law again. Voltage across R2 ay R2 0.90 divided by 0.003 is 2727.3 ohms. R2 is equal to 2.7 kilo ohms. Finding R4 here. So we need this pull down resistor to eliminate the possible leakage current or reverse voltage or switch floating, transistor hanging. And then at idle or series state, the current at IR4 is 1 milliampere when the voltage, when the base is operating in or open. So 1 milliampere is from here when the collector and emitter breakdown voltage IC is 1 milliampere when the base is open, and there's a collector emitter breakdown voltage, and there's a current flowing here na 1 milliampere. So we're using 1 milliampere here. So the breakdown voltage here, we now know that the voltage across here and this one is equal. See, voltage drop across the resistor here and the diode is equal to the R4. So we now know that equation. We know that voltage drop across I3 is 1.15, voltage drop across diode is 2.0. We now voltage drop across R4 is equal to 3.15. Ohm's law again. 3.15 divided by the current. Why is it 0.001 ampere from this idle state? We need to know this leakage current flowing, or just transpose it to the left, become 0.001 ampere. Okay, we need a current unit here, voltage or volt divided by ampere to get the ohms unit. So we got 3150 ohms. So 3.2 kilo ohms approximately. Well, I've got 3.3 kilo ohms available. So the circuit is now this one. See? There's no reverse voltage happening. Push the button, release the button, push the button, release the button. Seems the circuit is good. Okay, let us try to find out if we can build this in PCB. Okay, thank you for watching. See you in my next video. Thank you.